This video lesson will be talking about electronegativity and how it relates to polarity. Electronegativity is a periodic trend, just like atomic radius or ionization energy. The reason why we didn't talk about this periodic trend earlier is because this periodic trend is specific for when atoms are bonded to each other. The definition of electronegativity is it's the ability of an atom to attract electrons to itself when bonded to another atom. That's the important part of this definition, is it needs to be bonded to another atom. Now, there is a way we can quantify this, and that's using the Pauling scale. So let's go ahead and take a look at what this trend looks like when we're looking at the periodic table. If you take a look at the periodic table, you can see that the trend of electronegativity increases as you move from left to right, as well as it increases as you move from the bottom to the top. Remember, you can explain this using effective nuclear charge as well as number of shells. The reason why the electronegativity of an element increases as you move from left to right is because, remember, because the nucleus is getting more protons, that means the effective nuclear charge is increasing. Thus, the nucleus is stronger and can attract electrons to itself. As you move from the bottom to the top, the reason why electronegativity increases is because there are not as many shells. And so because there are not as many shells, the nucleus does not have as much shielding, and therefore it can pull electrons stronger. Now, according to this trend, the highest element of electronegativity would be the element fluorine. Helium, and as well as neon or argon, are not included in the trend. The reason why is because these elements are noble gases, and therefore they don't have a high capacity to attract electrons to itself. So fluorine is going to be our most electronegative element, and if we reverse the trend, francium will be the least. Now on this screen right here shows the Pauling scale. This is just one Pauling scale reference. You might notice that if you look at other textbooks or other sites, the numbers might be a little bit off, but it gives us the relative range of where the numbers lie. Notice the highest value for the Pauling scale is 4, and that belongs to fluorine because fluorine is the most electronegative element. The least number on the Pauling scale is 0.7, and that belongs to elements down here such as cesium or francium because these are going to be the least electronegative. Remember, electronegativity is defined as the ability of an atom to attract electrons to itself when it's bonded to another atom. So for example, when fluorine is bonded to another atom, because fluorine is highly electronegative, it's going to have a high tendency to want to steal electrons. Now, are you going to be expected to memorize all these numbers? No, it's just not necessary or possible to have to memorize all these numbers. But there are a few elements I would like you to be aware of and commit to memory. Those elements are these 6: fluorine, oxygen, nitrogen, carbon, boron, and then finally hydrogen. The reason why is because these elements pop up a lot, and so it's probably best to commit them to memory. The nice thing is, if you notice, it does increase as you go from fluorine and then to the left, and it increases by 0.5. And so that's a good way to remember how those numbers are going to be memorized. And then hydrogen over here is 2.1. That's kind of an oddball one you'll have to just know. Knowing these ones by memory are going to help a lot. Now I like this view here because this shows a 3D version of the trend. Notice as you move up a group, like for example group 1, group 2, and so on, electronegativity does increase, as well as electronegativity is going to increase as you move from left to right. Notice those highly electronegative elements are over here. Now notice there's some variation. It's not necessarily always going to increase in a steady fashion. For example, you can see there's some discrepancies here in the middle. A reminder that periodic trends are just that, they're trends. There's always going to be some exceptions there. But the main idea is that elements do increase their electronegativity as they go from left to right and as they go from the bottom of a group to the top. Notice the most highly electronegative elements are fluorine, oxygen, and nitrogen. Chlorine is as well, but chlorine is not going to be as highly electronegative since it's going to be in the third energy level. Alright, now that we have a basic idea of electronegativity and what it is, let's go ahead and apply it. Let's take a look at 3 bonds. I want to look at the molecules H2, HF, and then NAF. Obviously, there's some sort of bond going on between these elements, otherwise there wouldn't be actually a bond taking place. So we can kind of roughly visualize the bonds looking something like this. So there's the hydrogen bond, there's the hydrogen-fluorine bond, and then there's the sodium-fluorine bond. All right, now if we take a look, these are what we call electron density maps. Basically what they're doing is they're showing where the electrons are essentially residing in the molecule. Those can be shown in red. You'll notice for the hydrogen-hydrogen molecule that the electrons are pretty much existing right there in the middle. You can also notice there's a uniform composition to the shape of the molecule. This is indicating visually that there's an equal distribution or equal sharing of the electrons. If you look at the second molecule, HF, the electrons are residing over here closer to the fluorine. And as a result, it kind of looks like there's like an oblong or egg-type shape to this molecule. Finally, over here, the molecule NAF, this is going to be not only the electrons are over here by the fluorine, but there's almost such a pull that you can kind of see there's an indent in the molecule. Now we're going to be able to explain this using electronegativity and how it can relate to polarity. Essentially, there are three different types of bonds. There's ionic, there's polar covalent, and then there's nonpolar covalent. Being able to identify what type of bond is taking place between two elements comes down to the electronegativity differences between those two atoms. So what we're going to do is we're going to take a look at what is the difference in electronegativity of these two atoms. If the difference between the two atoms is lower than 0.5, the bond is classified as nonpolar covalent. Basically what that means is the atoms are essentially equally sharing the electrons that are in the middle. If the difference is between 0.5 and 2, the bond is considered polar covalent. What this means is covalently, the electrons are still being shared, but they're being shared in a polar fashion, meaning that there's going to be an unequal distribution of sharing. One of the atoms must be pulling the electrons stronger than the other. Finally, if the difference is greater than 2.0, the bond is essentially ionic, since there's really not any sharing going on. So let's apply this to our three molecules that we were looking at before. So let's go ahead and take a look at the first molecule, HH. All right, so I want to figure out what kind of bond is taking place between these two atoms right here. And so what I'm going to do is I'm going to take the difference in electronegativities. Hydrogen has an electronegativity of 2.1. So this electronegativity is 2.1, as well as this one. If you take the difference between those two numbers, obviously the electronegativity difference is going to be 0. 0 is less than 0.5. And so this bond that's taking place between these two hydrogen atoms right here is going to be classified as nonpolar covalent. Now, not only is it considered nonpolar covalent, but because the electronegativity difference is exactly 0, this actually would be considered what we call true nonpolar covalent. A true nonpolar covalent means that truly the electrons are existing right smack dab in the middle. This is only going to take place when the electronegativity difference actually is 0, indicating that the electronegativities must be the same, and oftentimes this means that it's the same element bonded together. Okay, let's take a look at the second molecule, HF. We know the electronegativity of hydrogen is 2.1 and fluorine is 4.0. The difference between these two numbers is going to be 1.9. According to our rules that we just read about, this falls under the second bullet, meaning it's between 0.5 and 2.0. This means that the molecule is going to be polar covalent. Now remember, what does polar covalent mean? Well, it's covalent, which means that the electrons still are shared, but they're shared unequally. That's what polar means, it's unequal. And so in all reality, the electrons are not existing exactly in the middle like they were before. They're probably existing, in fact, they are existing closer to fluorine, since fluorine's the more electronegative element. It's pulling stronger. And so the electrons are probably going to be a little closer, and so I might draw them in such like this. Because the electrons are existing a little bit closer to fluorine, we would say that there's actually a partial charge that's being generated here. What that means is fluorine has a slightly negative charge and hydrogen has a slightly positive charge. The S-shaped looking thing that I just drew right here is actually a lowercase delta. It looks like the letter S with a loop on the end. That delta symbol means slightly or partially. So hydrogen is partially positive because it has a sense of absence of electrons, whereas fluorine is partially or slightly negative because it has a closer proximity of the electrons on its side. But the idea is that they're still shared in between, they're just shared unequally. Now there's another way we can show this separation of charge here. This is the first way, which is what we call delta notation, because remember that stands for delta. The other way is what we would call a bond polarity arrow. We always have the polarity arrow facing in the direction of the more electronegative element, which in this case is fluorine. So what I would do is I would actually draw an arrow above the bond with the arrow facing towards fluorine. Notice on this side, I make it look like a crosshatch. It makes it look like a positive sign, so make sure you put that there. And so this is what we call a bond polarity arrow. It shows the direction of pull of the electrons. All right, let's look at the last one. Fluorine we know is 4.0 electronegativity, and sodium, if you remember, it's 0.7. It was kind of towards the left and towards the bottom there. Actually, I think I think it's actually 0.9. My bad. So sodium is about 0.9. But either way, if you take the difference between those two numbers, it's going to be 3.1. That's definitely higher than 2. And so what this means is the electrons are not being shared anymore. The electrons are pretty much residing completely on the fluorine. What that means is there's such a separation of charge that we no longer consider it covalent. Those electrons are not being shared. In fact, it's now pretty much considered ionic. And this is actually how we know bonds are ionic. An easy way of figuring out if it's ionic is looking at if it's a metal and a nonmetal bonded together. But an actually more accurate way of identifying if a bond is ionic is to look at the differences in electronegativity. And that's why a lot of times when you see that it's a metal and a nonmetal bonded together, the differences in electronegativity are so great, that's why it's considered ionic. When you see this indentation in the density map of electrons, that's pretty much going to assume that it's an ionic character because there's such a separation of charge that it's no longer slightly positive or slightly negative, but it's pretty much all positive on one side and all negative on the other side.